Hello, my name is Arvin. I'm doing my master's in electrical engineering here at UL Lafayette, and at the same time, I work as a graduate research assistant in Power System Care Research Group with Dr. Faisal. Today, I'm presenting my design and my research. As you can see, I have my testbed here, but before diving into my testbed, I would like to give an overview of the problem I'm tackling here. As a case study, I have DC-DC converter. Actually, I have buck converter here. But what is the DC-DC converter? What are the applications? They are widely being used in EVs, in microgrids, and more to step down or step up the voltage. For example, let's say you have a fixed source voltage, but you need a different output voltage. You can use these converters to convert the voltage at the source side to the value that you want to have at the load side. I'm proposing an AI-based controller to control the dynamics of these converters. The initial results are indicating that my proposed controller could outperform the conventional controllers. Let's see what I have in my testbed. Now let's take a closer look at my circuit. I'm replicating the circuitry of a buck converter as shown in the diagram in the top right corner of the video. Here is my testbed featuring the DC-DC buck converter. In this setup, as you can see, I use a programmable source providing 24 voltage DC as the input. This allows me to control the input parameters precisely to meet the specific conditions required for testing. The key components of the buck converter, as you can see again in the diagram, include inductors, capacitors, and diodes, forming a filtering and control circuit. The most critical element, however, is the switch. By controlling this switch, essentially by turning it on or off, we can adjust the output voltage to the desired value. Here, as you can see, I use an IGBT to replicate the switching behavior. The switching times, or how long it's on versus off, is controlled by a pulse width modulation that we call it PWM signal. This signal determines the duration of the switch's states, allowing us to control the output voltage precisely. For the load, I use programmable load, which provides flexibility and safety by allowing me to set limits and replicate different scenarios. I mean, you can program it to act as an EV battery, CPL, constant power load, or other applications. Additionally, this load has a built-in data measurement, so I don't need separate devices to track the data like voltage and current. Now let's take a look at the control circuitry. As you can see, I use a Raspberry Pi 5 as a controller to implement the AI-based control method. Specifically here, I use reinforcement learning, that we call it RL. RL is an AI approach that adapts based on interaction with its environment. To control the circuit, the Raspberry Pi collects the data from the load such as current and voltage. Since the programmable load provides only analog data, here I use microcontroller that we call it MCP to convert this analog data to digital, allowing the Raspberry Pi to process it. Once the data is digital, it's sent to a server on my computer using TCP communication protocol. All devices in this setup communicate indirectly through this server. This approach enhances the security and ensures reliable data exchange. Upon receiving the current and voltage data, the Raspberry Pi processes these observations through the RL algorithm, which outputs the specification for the PWM signal. This signal is crucial for controlling the switch and ultimately the output voltage. The Raspberry Pi calculates the precise PWM specification, tailoring them based on real-time data to achieve optimal control. Finally, the PWM specifications generated by the Raspberry Pi are sent to the NI Mario 1900, which will take care of making the actual PWM signal according to these instructions. The Mario and Raspberry Pi maintain communication through the server, ensuring a seamless and reliable control loop across all components. Now I will run a test scenario to evaluate my design's performance. To make the test more impactful, I will introduce a fault during operation. This allows us to observe how my controller responds in comparison to a conventional controller, which I will refer to as a baseline control. Great, let's see the performance. As you can see, my proposed controller maintains the output voltage at the target level of 12 volt. When I introduce a fault by changing the source voltage, the controller quickly detects the change. Within a few milliseconds, it adjusts and brings the output voltage back to its steady state value. Finally, here is the final comparison with PID-based controller, which is commonly used in industry. As you can see, my proposed controller outperforms the PID by restoring the voltage to its steady state just a bit faster.